Evening, good morning, and good noon, all of you. I am Dr. Mehrchand and moderate this session today. Welcome all of you in this fourth session of the fourth day of Faculty Development Program. Today's speaker is Dr. Dr. Abubakar Hamid Denilami. He is lecturer in the Department of Economics, Faculty of Social Science, Bayero University, Kano, Nigeria. His research interests involve agricultural economics, applied microeconometrics, energy and environment economics, microeconomics, and applied economics. He has published numerous research publications in reputed journals and attend various training programs and deliver invited talks in the conference as well as in the workshops. So now I would like to invite today's speaker in this session. I hope his expertise will be very helpful, knowledgeable, informative to all the participants who are attending this session. There are many participants who are attending this session through live streaming also. Welcome, dear professor, in this session. Now I am going to assign you a presenter of this session. Yes, dear professor, now you are a presenter in the session. You can mute, unmute, okay, and you can control all the things. Now I want to hand over my mic to you. Welcome and please start your lecture, dear professor. Welcome in the session.
Okay, thank you very much, Professor. Also, I'm welcoming everybody that is participating in this workshop. We are hoping to have a H3 presentation, and so I'm now going to share my screen with you so that in order to start the presentation. So I don't know whether you can hear me. This is the outline for today's discussion. As already known, we are going to cover these topics now, inshallah. Linear regression model, which consists of OLS estimators and multiple linear regressions. Also, the second topic to cover is post-estimation tests. That is relaxing the assumptions of the classical model, meaning that what happens if you did not meet the assumptions as far as the OLS model is concerned. Then we are going to also conduct hypothesis testing to see how we test hypotheses, especially using ANOVA, and also to see how we report results using Stata. Then lastly, we are going to conduct a dummy dependent variables regression. So because in this case, the dependent variable is of two categories, which is usually different from OLS. So these are the topics we are expecting to cover now. I hope we are going to have good and wonderful presentation. So actually, I will start with the first one, which is linear regression model. So when you talk about a linear regression model, you want to, it's a regression model that you want to estimate the relationship between two or more variables. One at least is a dependent variable and the other, at least the other one, or if you have many independent variables. So that is why you have univariate analysis whereby you have only one dependent variable, one independent variable, and you have multiple regression whereby you are assessing more than one variables. So the main target here is to conduct an estimation in order to ascertain or estimate or assess the relationship between the independent variables and the dependent variables. You want to ascertain how the independent variables influence the dependent variable, whether it's in positive side or a negative side. Also, you want to ascertain whether it is significant as far as influencing the value of the dependent variable. For example, you have a quantity demand, so you want to ascertain what are the factors that influence the demand of a particular commodity. So this is the target of OLS, or regression analysis, to establish the relationship between two or more variables. Then again, OLS is built on some assumptions, which are before you estimate OLS, you have to know that there are some assumptions that serve as the guideline for estimating a valid OLS model. These assumptions, we are going through assumptions quickly in summary. We have assumption number 1, that is linear regression model. The model must be linear in the parameters, meaning that you will not have square parameter or polynomial parameter, though the variable can be square depending on the nature of the relationship, but as far as the parameters is concerned, the model must be linear. Number 2, x values are fixed, meaning that the values of the independent variables are determined outside the relationship. The relationship only determines the value of the dependent variable, but for the value of the independent variables are determined outside the relationships or are given based on the data you collected. Assumption number 3, the model has a zero mean value of disturbance, meaning that the average value of the random error is 0. This is because if you are estimating OLS, you are trying to find a model that best fits that has a perfect fit of the reality. So if you estimate the model, definitely there has to be some error. So some will be negative, some will be positive. So at the end of the day, if you add the error together, if you try to find the mean of the error, it will be 0. Then assumption number 4, the model is homoscedastic, meaning that given the value of x, the variance of the random error is the same for all observations. The expectation is that the variance of the random error should not be changing. If you violate the assumption, it means that we are going to see when we are going to conduct post-estimation tests, how we test for this, whether we meet this assumption or not. Then assumption number 5 is no autocorrelation between disturbances. So this one especially is for time series data, not for cross-sectional data, because our focus now is cross-sectional data. So it means that over the period of time, the error time disturbance, there is no correlation between the error disturbance for a time for last year and for this year. Assumption number 7, the number of observations must be greater than the number of some parameters to be estimated, meaning that the sample size must be greater than the number of variables in the model. If not, then you cannot be able to even estimate. You cannot conduct the model estimation using Stata. You cannot. It's not possible. Therefore, anytime you are trying to estimate, you must make sure that the number of variables is greater than the number of observations is greater than the number of variables. Especially some scholars give some rule of thumb. Some are saying you should make it at least 5 times for good estimation. Some say no, you can make it 10 times. So depending on the circumstance. Assumption number 8, it says that the variability in x values, meaning that the values taken by independent variables are what? There is a variability. There is a variability, meaning that when you collected data on different variables, data must be different. Individual observations in the data must be different. It must not be the same. For example, if you have income, you say $10 for all the observations, no variability. Estimation cannot take place. Estimation can only take place if there is variability. It takes some values, different values. Then assumption number 9, the regression model is correctly specified. The assumption is that you did not conduct or in the form you did not conduct a specification error, whether by omitting a relevant variable or by putting an irrelevant variable. So therefore, the model must be correctly specified. We are going to see during the cost estimation test how you can meet with this assumption. The last assumption is there is no perfect multicollinearity. That is the relationship among the variables must not be perfect. If there is a relationship between independent variables, say you have the dependent variable, for example, is demand. The independent variables, for example, we have income and we have price. So the assumption is that the price and the income that assumed to influence the demand must not be perfectly related. If they are perfectly related, then you cannot estimate using Stata. The Stata can automatically remove one of the variables. But if they are not perfectly related, they can be related, but at a lower level. If they are highly related, also there's a problem. So we are going to see how to conduct the test of multicollinearity and also the solution for this. So this is in summary the 10 assumptions on which the estimation using OLS is built upon. Then we move to the condition of estimating OLS. We have seen the assumption. So what is the condition? So what is the cost? I have OLS that I just want to use OLS like that. It's not like that. You must meet the condition of estimating OLS by how, number one, based on the data you have, the dependent variable must be quantitative. If you have a qualitative dependent variable, you cannot estimate OLS. And if you estimate OLS, it means you are estimating linear programming model, as we are going to see the model, which is not a good model per se. So the condition is that you must have a quantitative dependent variable, meaning that it's not of 2 categories, 3 categories, but rather it's a quantitative. Maybe income, you have income of $10, $20, $100, like that. Or maybe age, for example, 20 years, 30 years, 25 years. So at least the dependent variable must be what? Must be quantitative in nature. Though the independent variables can equally be quantitative or qualitative, it's all the same. Secondly, if you have the quantitative dependent variable, you have your data, but the data is censored. There is the data on, you have a sensor data for the dependent variable, meaning that there's a kind of truncation at a particular point. So also it's not good for you to use OLS, but rather you should use another model, popularly known as a turbine model. If you use OLS, it's not good estimation if you have a sensor data for the value of a dependent variable. So this is about OLS, the condition of estimating OLS. So we assume that we meet the first condition is that the dependent variable is quantitative. The second condition is that our data, there is no censoring regarding the data on our dependent variable. So now, before you go to direct estimation, at least you need to see how we specify OLS in our, maybe if we are writing our paper, or if we are writing our thesis project. So this is how you specify, as we can see. I hope as you can see from my screen, y is the dependent variable, and the other side are the various independent variables. You have beta naught, which is the intercept, and you have xi variables and the rest. So these are the independent variables. So first, you specify your theoretical model. This is what is known as theoretical specification for OLS model. Then you specify your model to estimate. So in this case, we are going to use the data for fertilizer consumption. So fertilizer demand. So you can see that the model is the empirical model is we have dependent variable, which is the demand for fertilizer, and the various independent variables. That is the other factors which we expect to influence the quantity of demand for fertilizer by a farmer. We have gender, M status, education, household size, and so on and so forth. So this is how you make a empirical specification of your OLS model, either in your paper or in your thesis and so on. So now let us use the Stata to import our data so that we estimate the OLS model. So this is my Stata window. I just already I have my data open. So I will just copy. I will just copy the data and paste it. I check on the data editor. You'll see option edit. This one, data editor browse, you cannot paste it, but you can paste using this one, data editor edit. I click on it. Then I make sure that this box is in the first Excel. That is this one. I have point on the first cell. So I right click, I say paste. So I select, you see the starter is asking me, do you want to treat the first row as variable names or data? So you must say you must select this one. You want to treat it as a variable names. So as we can see, this is our data editor. So we can see the data. So we have to a little bit go through the data to see whether we can see a string variable. So we are lucky we don't have a string variable. A string variable occurs if one of the variables appears to be red in color. We can see all the data here, all the variables appeared black in color. So if one of them appeared in red color, it means it is a Stata recognizes variable as a string variable, which means that you cannot use it in the estimation. You have to encode it before you will be able to use it. But luckily enough, we don't have that. And usually this occurs if there is a problem in encoding right in your Excel. Maybe you put a comma inside the data, or you put some alphabet and so on. So now we have already entered our data. Now let us try to estimate. We need to now estimate our OLS model. So this is the command we use. You type your regress, then you select the dependent variable is fertilizer. The fertilizer demand, the quantity of fertilizer demanded or used by a farmer. So here is our dependent variable. We want to see what are the factors that influence the quantity of the fertilizer to be demanded by a farmer, for example. So already I click on it. So you can see that I have regress and I have fertilizer. So as my dependent variable, then I will select the various independent variables. So as we can see, we said we included income, farm size, for example, number of labor in the farm. Then we have years of fertilizer use experience. And we have, for example, fertilizer price or cost. And maybe we said number of expert extension visits. So now we have our dependent and independent variables on Stata on the command window. So as you can see the command break, then we type enter. So can we see, you can see this more is appearing, there's this more is appearing, so we can be able to say set more off. We want to off the more, so that anytime we type, we want to get a result, we just have one result automatically like that. So as we can see now, this is our estimated model, OLS model. So this is our estimated model, OLS model. From the table, we can see ANOVA table first, which is meant for joint significance test. This is number of observations. It means the total number of observations that is used in the model. So in the estimation, normally Stata use the total number that is that there is no missing value based on the number of variables are used in the model. For example, you can see the total observation data collected is 400 samples, but you see it used 70 something. Why? Because there are some missing values in one of or more of these variables. So normally Stata disregard the missing values and never use it in the process of estimation. So you can see this variables included in the model are jointly significant. So how do we know whether they are jointly significant or not? We look at the probability of the F value. So we can see this one is telling us that the variables that we included in this model are jointly significant. And we can see the R squared. This R square, it is trying to show us that the portion of the variability of the dependent variable explained by the independent variables. For this model, is indicating that 27% of variability of fertilizer use is explained by the independent variables we use here, such as income, farm size, and the rest. So this is about this. So we want to come down to the model now. This is the coefficient. This is the standard error, and this is the t-value, and this is the probability. So now, for us to know which of the variables is statistically significant, we just look at the probability. So if we can see now, we can see income is significant, but at 10%. Normally, we have significant level at 1%, 5%. In some cases, sometimes we allow at 10%, but sometimes some books just take 5% as the minimum level of significance, but at least we can have a safe window so that at least to have more number of significant variables, so we can use the 10% also. So if we can see based on this, the variable income is statistically significant at 10% level. And this farm size is significant at even 1%. If you want to know the level of significance, you just multiply this by 100. So since this one is greater than 5, if you multiply by 100, it's greater than 5, but less than 10, we can say that it is significant at 10%. While this one, if you multiply by 100, you see that it's even less than 1. So we say it's significant at 1%. Then look at the other variables. So only 2 variables in this case are statistically significant based on this model that we estimated, the income and the farm size. So this is the how we estimate OLS model. Now, assuming we are okay with this model, this is just for example, but at least larger number of the variables must be significant before you will be okay with the model. At least you need to have at least let's say 60% or 70% of the variables included, or less otherwise. So assuming we are okay with this model, now we need to take these results to our to what where we are working. Maybe we are working for our paper, or we are working for our degree thesis, either master's or PhD. So now we need to use we need to use outrect2 command in order to export the results in a way that we report them in a paper or in thesis, because this format is only used for appendix. You copy this one, you paste it in appendix. This is in the case when you are writing for your degree-oriented research, such as master's and PhD, or even undergraduate. So, but for the normal presentation, we need to use a command, SS outrect2. So we can see this. I will use this. So you can see I type outrect2 use it. So in this case, I'm using Stata 14. So for this one, I have to go back and copy the directory in which I want the Stata to save the results. If I'm using, let's say, Stata 11 or Stata 12, I don't need to copy for the directory. I will just type this outrect to using, I give the file name, I put comma, and I type word. Then it will go. But since I'm using Stata 14, in most cases, you find out that you have to copy the link. You have to copy the link through which the directory, sorry, not link, the directory which you want to save the, otherwise it will not work. So for simplicity, I'm advising that you create a folder on the on a desktop, on your desktop, and then you give it a single name, because sometimes you find out that if you give it double name, it's sometimes rejected. So you give it a single name. For example, I have a folder, I call it results, on my desktop. So I open the folder now. So I point out at the directory, I click on the I click here, you can see the directory, I right click and copy. I copy it. Then I come back to my Stata and I paste it. Then I write .doc. This .doc, it means that I want it to be in Word. Then I write replace. Why I'm writing this replace? Because I want the Stata to accept this result in case if there is other result, that in case I use the folder before. Because if I didn't write the replace, it is just going and append the result together with the existing result. It will just go there directly and merge the table. So as you can see, this is the command I use, outrect2 using, this is the directory and .doc. So I will just type enter. So you can see it means we are successful. So you can want to open this in onward. So you can see how it open, how it saves the results. and this is the format we usually report. You highlight and you copy and you paste in a particular word where you want to report the results. So this is about estimating OLS and reporting the results. And I say this command is usually from Stata 14 upward. If you are using Stata 11 and 12, you use outrect2 then you type the name, you put comma like this, outrect2 using, you say for example, results, comma, port. So in this case, if you are using Stata 11 and 12, it will go and save your work there. Sometimes you may not, if you are first time in using Stata, so if you put this outright, it will type that or recognize command. So in this case, you need to install it. You need to use ssc install outright2. ssc install outright2. So in this case, for example, if you don't have, we can see it is saying it is contacting the host and it is receiving. And we can see the final answer after checking the outrage2 consistency and verifying whether it is not already installed. They say that all files already exist and are up to date. So already I have been using it. But if you are using Stata for the first time, or if, for example, you just install your Stata in your system, actually you have to install it using this command as I did before. So this is about your OLS and reporting results. So as we say, OLS model should be one that is guided, one that is built on the previous assumption we highlighted. So now, how do you estimate? How do you ascertain whether you made this assumption or not? Whether you meet the assumption. So this is come to the word post estimation test. That is the reason why we conduct estimation tests in order to ascertain whether we meet assumption of OLS or not. So we can see, we can test for heteroscedasticity, we can test for normality, we can test for model specification, and we can test for multicollinearity. At least these are some of the basic tests you can conduct for estimation using OLS. So for example, if you want to test for heteroscedasticity, after estimation, you type after estimation, you type a start head test. A start head tests. So you can see Stata conducted for us Bruchpagan test for heteroscedasticity, and the null hypothesis is that the variance of the error term is constant, that is homoscedastic. So now we look at this value. If you want to conclude, we look at the probability value. So what happened here? We can see that the when we multiply this value by 100, we have about 59%. So it means that it is higher than at least the 10% threshold level, or even the 5% in some cases. So in this case, we say that we do not reject the null hypothesis of constant variance. We do not reject the null hypothesis of constant variance, and we can conclude that the variance is homoscedastic, or we already meet assumption of homoscedastic. So we don't have the problem of heteroscedasticity. So at this stage, for example, if after you test, you find out that you have the problem of heteroscedasticity, so this is not the end of your model, but rather you just need to rectify. You just need to rectify the problem. But before we rectify for heteroscedasticity, I want to highlight the causes, some of the reasons why heteroscedasticity arises. Probably presence of outliers. Outliers in the data, sometimes they are the causes of heteroscedasticity. For example, outlier is a variable, is an observation that has a wider difference between the rest of the observations. Whether it's too large, it's too far, the value of one variable, one observation is too far from the rest of the observations, or is too low compared to the rest of the observations. So in this case, we say there is outlier in the model. So if there is an outlier, probably it may lead to problem of heteroscedasticity. Another reason why heteroscedasticity may arise in Euler's estimation is the presence of skewness in one or more of the independent variables. As we did now, we say our dependent variable is demand for fertilizer, and independent variables consist of income, farm size, and so on. So when we look at variable like income, variable like farm size, definitely these variables are characterized by, in most cases, skewness. You find out that you have few people that have higher income, only few people that have higher income. Normally, income does not have normally distribution, or even the size of the land. You find out that there's a skew. It's skewed to some of the few farmers that they have. So in this case, if that happens in the data, so it may lead to problem of heteroscedasticity. Another issue is incorrect data transformation, because when we are, for the first time, if we are doing if we start our analysis, probably what we are supposed to start is data management. We need to check the data. We need to see the summary of the data, the descriptive analysis, and so on. So sometimes in the process of data management, we make some transformation. So sometimes the transformation may not be proper. So incorrect transformation of the data may also lead to what? May also lead to the problem of heteroscedasticity in the data. And then lastly, some of the reason why a researcher may face problem of heteroscedasticity in OLS is incorrect functional form, meaning that you have a model specification error. You probably issue whether the model should be linear, log linear, linear log, or sometimes you omit an important variable, or you over identify the model, that is, you put more variable that are than are necessary. So in this case, we may likely have the problem of heteroscedasticity. So now, assuming we face the problem of heteroscedasticity, how do we do in order to rectify, or is that we already finished, our model has stopped our estimation? No, presence of the heteroscedasticity cannot stop our estimation, only that we rectify for it by estimating robust standard error. So now I click on back my earlier command, so you can see the same command, the same variable, assuming I have problem of heteroscedasticity. So I'll just add comma and then type R robust. just type a robust. So in this case, you can see another estimation, and you can see that now even the number of the significant variable changes. So this, you can see, these are robust standard error. Robust standard error. This is the same coefficient as, if you look at the coefficient, you see that the values are the same. The values of the coefficient are the same, but only the value of the standard error changes. Here we have robust standard error, and this robust standard error, they are free from the problem of heteroscedasticity. And we can see when we use standard error, we can easily see that the number of significance and the level changes. Income that previously was significant at 10% is now significant at 1%. Farm size significant at 5%. You can see number of labor used in the farm is significant at 10%. So this model is better. So in this case, you are to report this model instead of reporting the previous estimated model, because this is totally free from heteroscedasticity. So as you can see, this is the remedy. What will happen if we try to test for heteroscedasticity weak? Let's see. Now say a start head tests. You can see the Stata said head test not appropriate after robust cluster, meaning that this is free from problem of heteroscedasticity. So you don't need even to test it. After this one, if you even try to test it, Stata will not allow you, you will not get appropriate results. So this is about heteroscedasticity. So another post-estimation test is test for normality. We assume that the data is normally distributed. One of the assumptions of Euler's is that the data is normally distributed. So how do we know whether we meet this assumption or not? By conducting a normality test. So how you conduct a normality test, for example, if we call back our estimated model, now we said predict E, you call them residuals. So now it means that you generated residuals for this estimated model, error terms. The residuals is the difference between the actual Y value, dependent value, and the estimated dependent value. Based on this model, we were able to generate the residuals. Let's check our data editor. We can see that we have this as one of the variables. This is the residual. We can see we have generated residuals, a random error. Some are positive, some are negative. So now, then we type another command in order to know whether we made the we achieve or whether we meet test for normality or not. We said K density E now we give Stata to draw command to draw the distribution, to show us the distribution of our random error. So while it's bringing the curve, let us use another command. So we can use another command. There is okay, so now we can see this is the normally distributed curve. and this is our estimated residuals. So you can see that at least the difference is minimal. So we can assume that we meet this assumption. So this is an analog way of saying it, the graphical way. So we can use a digital way, or we can for figure, which will give you exact whether we meet or we don't meet. So we can type this in tests after estimation. So this is Cameron and Trivedi test. So this test has advantage. Not only you test for heteroscedasticity together with test of normality. So you can see, you just look at this, you can see that you already pass. You perfectly pass the test. Or you can see individually, this is heteroscedasticity, and you can see the value is that we do not reject the hypothesis, the null hypothesis that we have a homoscedastic. And we can see the skewness and kurtosis test, and the p-values are also insignificant, meaning that we have our data is normally distributed. So in this case, we say that we meet our normal distribution. So in case if we did not meet the assumption of normality, probably by adding the number of data, probably we are using small sample size. So if you add the number of sample size, maybe you add more data to the previous one you have, at least you may wipe away, especially due to the issue of central limit theorem that said at least data tend to be normally distribution as if the data is large enough. Or you can make some transformations such as logging the variables, at least your data will be normal. So this is about normality test in OLS. We have seen the two ways. We can use graphical test and we can use this Cameron and Trivedi. And it's as well in us anytime we are using this we are using OLS, so we should use Cameron and Trivedi because it's easy to pass. Because even the tests are of different levels. Some you hardly pass the test, meaning that always if you can use that test, they say that you did not pass. For example, if you use this command, so you see the probability is significant. You did not pass the normality assumption. It's very difficult. So therefore, but you don't need to use this one, you just use this Cameron and Trivedi, and that's all. So this is about test for normality, test for heteroscedasticity. Now we move to another post-estimation test, which is test for model specification. If we can remember, we said that OLS is assumed to be, the model specification is assumed to be free from error, meaning that there is not a limited variable problem, meaning all the variables that are significant and we're supposed to include in the model are included. And also we did not over-identify the model, meaning that we did not incorporate unnecessary and irrelevant variables. So if you want to conduct the test, so you can use this command. After estimation, so we say OV tests. So we can see this is Ramsey reset test. The model, the null hypothesis said that model has no omitted variables. So we can see based on the probability value, we do not reject the null hypothesis, and we concluded that we have no problem of error specification. We don't have omitted variable case. So we have another way of conducting model specification test using link test command in Stata. So we can use this link test. Same after observation, after estimation, you conduct this link test. We can see this. Look at this. You have hard square and constant. So you look at this hard square, you come and you check the probability of the variable hard square, this one. So based on this, you make your decision. Whether the null hypothesis also said that what? The null hypothesis says that the variable, the model is correctly specified. So in this case, we do not reject the null hypothesis, and we concluded that the model is correctly specified. So you have option whether to use OV test command or use link test command. You can check your model specification error, whether you have met that assumption or not. So why do you have model specification error? Why do you have? In some cases, model specification error is usually caused by omission of relevant variables. Some variables that are very relevant, especially probably in the theory, you are supposed to, there are many theories that says it's relevant and argue that so variable is relevant in explaining so variable. But you omit it, you did not include it. So this may lead to omitted variable or error, model specification error. Also, inclusion of unnecessary variable may lead to also error, model specification error, whereby a variable that is totally irrelevant to the dependent variable, but you include it, so may lead to also model specification error, or sometimes adopting the wrong functional form of the model. For example, you use square for the independent variable, whereby ideally the pretest indicated that there is no relationship between the square of the variable and the dependent variable, but you square it, or you use polynomial, or sometimes you try to use log linear, which is supposed to be just linear, or log, depending on. So this may also cause model specification error. Some error measurements when we are doing error, because you need to if it is what it is, so you need to change the questionnaire here. We don't say that just develop a questionnaire, but rather we adopt questionnaire and modify for validity in order to avoid this kind of measurement error. So these are some of the causes of a model specification. So what happens if you fail to meet this assumption to pass this test? But our own case we already passed. So actually, is the process is a trial and error. So you have your data already. You know that some variables you did not include some variables, so you include them and you see. You also check the model fits. So if you pass the test, then if you did not pass, you also include or change. Or sometimes you drop a variable that you see that is less relevant, and then you conduct the test again. Thereby, you come to ascertain whether you specify also whether you corrected your model or not. So actually, we dealt with this by random and error process. You add, you remove, you add, you remove until you meet. However, the process of adding and removing will not be just randomly guided, but it has to be guided by the objectives of the study and the theoretical background of the study. So this is about model specification test, which is one of the tests for which is one of the post estimation tests and one of the assumption of OLS. Then we are going for the last one here is a test for multicollinearity. Test for multicollinearity. In OLS, if you call back our assumption, we assume that in assumption number 10, there is no perfect multicollinearity among the independent variables. So if they are perfectly related, it means automatically the two variables that are perfectly related in the model, they are doing the same function in the model, they are doing the same work 100%. It means one is dormant. So if you are trying to estimate that kind of model in Stata, automatically Stata is going to remove one of the variables, and you will see that it reports that so variable is removed due to multicollinearity. But however, in some cases, the relationship is not perfect, but rather is very high. It's very high. It's also undesirable. A relationship to be very high is also undesirable. So that is why we want to check for that. If you check for that, in this case, if it is very high, Stata can run the model for you. And for both variables inside the model, can run it for you. But the two variables are highly correlated, meaning that they nearly perform the same function in the model, which is not desirable. So in this case, Stata can run the model. Like if the relationship is perfect, Stata automatically remove one of the variables, and you will get to know that in the results, Stata shows you that so variable is removed due to multicollinearity. So now, we now conduct a test for multicollinearity of our estimated model. We type VIF. That is variance inflation factor. It's a test for multicollinearity. So in this case, look at these values. We are looking at these VIF values for each of the variable. We can see all of them, the values are low. The values, they say that the values that are below 5 is considered to be low. So values that are from 5 and above, close to 10. So it means that there is need for attention for some of doing some transformation in order to limit the impact of multicollinearity. But however, as long as one of these values is 10 and above, it means there is problem of there is high collinearity, and you need to remove one of the variables so that to avoid the problem of multicollinearity. So in this case, we don't have problem of multicollinearity, and we just report this result of VIF test in our data analysis section. So now, what are the causes of multicollinearity? Normally, method of data collection actually may cause multicollinearity. That is, in the process of data collection, you are just collecting data over a limited range of samples. You limited the range of samples. So if that is the case, we may likely have some similarities which may lead to issue of multicollinearity. Also, model specification error may result, because in some cases, you include irrelevant variable or you remove relevant variable. So in this case, multicollinearity may arise. Sometimes over the timing model. Over the timing model, the model that whereby the number of observations is higher than the number of is lower than the number of variables. In this case, you cannot even estimate the model. It's unestimatable. You cannot estimate the model. It's not possible. So another reason why multicollinearity comes into it is that you generate a variable from another variable. So this is through your data analysis. You have a specific target. So you feel that square of a particular variable is relevant. So in this case, you generate square of a variable, you include it in the model, and also that variable, initial variable is there, its square variable is also there. So in this case, you may likely to have issue of multicollinearity. Or you create an interaction variable, two of your variables that are already in the model, you interact them also. So maybe let us consider generating square of one of the variables, let's say income. We generate income square is equals to income is equals to income square. So we can see three missing values generated. So if we go to our data editor, we can see that we have income square here. And there are three missing values in that in the data. So now let us call back our estimated model and we add the variable income square. So let us try and conduct the VIF test and see what happened. So can you see this is too high? You can see the relationship between income and income. You can see the value of income is high now, unlike before. Income square is high. See, this is signaling, is indicating that there is they are performing nearly the same work in the model. But how do you do if you have a specific target of having this and these variables? Definitely, you know, income of the farmer must have an influence on his demand for fertilizer. If you have a target, you have a reason of including income square. So in this case, you have no option than to continue like that. You should not mind. And nevertheless, this one is lower. Sometimes you get some value 70, 30, 40 something. But despite that, if you know the value that is generated from another variable, so indicates higher value of VIF, so you just ignore that higher value, or you conduct the VIF test before including a model, before including the newly generated variable. So just like we should report the other VIF, this one, we can report this one, despite that in reality now this is what we have. But we can report the other one before we included this one, because it's well known that this and this must be related, must be highly related, because one is generated from another. But we have a specific purpose of doing that. So this no problem. We can continue with our model. despite these high values. And this is not even severe. We said it's less than 10. When it's less than 10, there is no problem. Actually, you can manage to continue your estimation, and nothing is going to affect the validity of your estimation. So this is about the post-estimation test, and these are the basic post-estimation tests you may want to present using Euler's model. You have to test for heteroscedasticity, test for multicollinearity, to test for model specification, and to test for normality. So after post-estimation test, and we make the necessary corrections. So what is going to happen is interpretation. Interpretation. Now, this is the results. As we can see, for example, we reported this result. Now, how do we interpret the results? As we can see, how do we interpret results? And so, or before here, we can say there are some guidelines for building your regression model. These are some of the guidelines given by scholars while building regression model. They say that make sure all relevant predictors are included. These are based on your research question, the theory, and your knowledge on the topic. You may have, as a researcher, you may have a prior knowledge on the topic and the relationship of the variables. So make sure that all the relevant variables are included in the model. So consider the possibility of adding interactions if that is the case. You possibility, if you can add, if there is possibility, you can add interactions. For example, in our model, we can see the interaction of income and farm size. That how the influence of these two variables together determine the fertilizer demand. So a farmer with higher income and with farm income, farm size, what will be the impact? Or lower income and lower farm size, for example, what will be the income, the impact of that? So also they say that you should consider the following as a strategy of keeping or dropping variables in your OLS estimation. For example, an independent variable is not significant and it has the expected sign. The expected sign is the a priori expectation you develop on variable. For example, now I put income in this estimation. My a prior knowledge is that income has a positive relationship with fertilizer demand. Higher the income, the higher the demand of fertilizer. Or I put fertilizer cost, price of fertilizer. The prior knowledge is that the price of fertilizer has a negative relationship with fertilizer demand. The higher the price, the lower the quantity demand. So in this case, even if it is not significant, but it is carrying the expected sign based on the prior knowledge, so you should keep that variable in the model. You should not remove it. Also, they said the variable is not significant and does not have the expected sign. That variable is not significant in the model and the expected sign is not based on a priori, does not conform to your a priori knowledge or a priori expectation. In this case, you drop the variable. For example, if in this case you can see fertilizer costs, we don't have. You can see the sign is positive, and a priori knowledge indicate that it is negative and it's insignificant, they say that you should drop it. But though in theory you may have strong argument of putting fertilizer costs as part of the predictors of fertilizer demand, because really definitely price must be number one factor in determining fertilizer. So probably this may be due to the fact that the cost is nearly the same, because this data is based on the price per 50 kg bag. So the variation is very limited. That is why. But that is why if you can generate square of this variable you add, definitely you can see that the sign of this may change. So in this case, if you don't have strong argument, you can remove it. But if you have strong argument like this one, especially you are estimating the timing of demand without estimating price, I think your estimation, your model is incomplete. Theoretically, the model is incomplete. So you may not. But if you don't have strong argument, you drop it. And you cannot say that you are going to change the sign. As a researcher, after you do the necessary data editing and estimation, you follow the good step, you estimate. You must report the results based on how you get it. I cannot say that I will maneuver and just add negative here because there is no way. No, it's not possible, but I may provide an answer to this, as I said earlier, probably due to the fact that the price is almost the same or something like that. We may have an explanation to forward the reason why you get something like this. So they said that predictor is significant and has the expected sign, keep it, meaning that it was found to be statistically significant at either 1% or either 5% or 10%, as the case may be. So, and the sign, you are expecting the sign to be positive and it appears to be positive, then you keep it. Just the way you have in our model here, the income variable. We have for this one, we have farm size, for example, where it's positive and is significant. So predictor is significant but does not have the expected sign. So you review, you may need more variables. It may be interacting with another variable in the model, or there may be an error in the data. So you did your estimation, you find out that it is significant, but it is carried out, it is contrary to a priori expectation. So in this case, you have to review, you have to include more variable in the model. You have to, in order to see that the science has changed. In some situation, you may you can argue, especially we in social science, in many cases we have way of explaining. If it is positive, we have an argument to say why it is positive. If it is negative, we also have an argument to say why it is negative. So it's not much a big deal. So this is the guideline for keeping or dropping variable from your OLS model. Then you come to interpretation of OLS model. How do we interpret OLS model? So basically, when we are trying to interpret the model, we need to sense in our interpretation. There is need for sensing these 7 issues in interpretation. When you are trying to interpret your variable, your coefficient of a variable, significant variable, so there is need for sensing this. It's not that you write this boldly, but rather in the course of reading your interpretation, we had that we see that you highlighted the variable. You also explained the level of significance. You also highlighted the dimension of finding, the magnitude, a priori expectation, implication, and previous studies. This variable highlights, you are highlighting the meaning and the measurement of the variable. This level of significance, you are trying to say whether it's significant at 1% or 5% or 10%. Here you see whether the dimension, whether it's positive or negative. The magnitude is somehow closer to the dimension. Whether increase in the variable will lead to increase. If it is positive, it will increase. If it is negative. So what is this magnitude? Whether it's conform to a priori expectation or not. The findings of the variable, is it in line with your priori expectation or not? Then after that, what is the implication of this finding? Then you also explain whether it is in line with previous studies or not. So this is how you interpret. For example, we can take in our model, we can take farm size. For example, if I want to interpret farm size, after making introduction of the interpretation by saying that a table so above consists the estimated result of the demand for fertilizer. This is, and there's the model indicated that the variables are jointly significant. So you have to mention this first, jointly significant at so percent, at 1% level, indicating that the variables jointly have impact, significant impact on the demand for fertilizer. Then here you are just to explain only the variables that are significant. So you take, for example, variable by variable is another way, though there are different way of interpretation, but it's another way you take this variable, for example, farm size. Say the coefficient of this variable represent the size of the farm owned by a farmer, which is measured in hectare. So you see that you highlighted the variable. The coefficient of this variable was found to be statistically significant at this one at what? At 1%. So you see, you already indicated the level of significance. The variable was found to have a positive relationship to the quantity of fertilizer purchase or demand. You can see you already set the dimension that an increase in farm size will lead to increase in the purchase of fertilizer by farmer. For example, a 1 hectare increase in farm size will lead to increase in fertilizer demand by about 0.50 of kg bag. Based on these results, by about 0.1 or 50 kg bag. You see, this variable is in units based on the number of hectare. So increase in the size of farm ownership, farm size by 1 hectare will lead to increase in the fertilizer purchase or consumption by about 0.150 of kg, because the dependent variable was measured based on the number of 50 kg used. So assuming this is in log, so it's like elasticity. 1% increase in the farm size will lead to 1% increase in the fertilizer demand, and so on, depending on what is the value here when you make this to be log and this to be log. Probably we can decide to do that. For example, we call back our we generate the log value first. L farm size is equals to log farm size. So already I have it in the data, is generated. So I can give it another name. Let me add this ln. So you see it has generated log. So if we go to the, you can see this is the farm size. So you see this already, it is there, it was here. So you can see they are the same thing. I have L farm size, so they are the same thing. So now, for example, I decided to include it in the model. Sorry, I did not generate the log value of the dependent variable. Probably we are having the log value of the dependent variable. This is the log value. So we don't need to generate it again because already we have seen the command of how to generate the log variables. So we just estimate this and add this L. So this is, we can see this is the log value and this is also in log value. But now it's not significant. So assuming this is significant and we want to explain this. So here is just an elasticity. We just say 1% increase in the size of farm ownership will lead to 0.13% increase in the demand for fertilizer. So it means that the demand for fertilizer is inelastic in nature. 1% increase in the farm size will lead to 0.13% increase in the quantity of fertilizer demand. So this is how we interpret if it is a log. That is, the dependent variable is in log and this one also is in log. So we are still on the interpretation. So we are trying to explain the magnitude as before. We said 1 unit based on this model, 1 unit increase in the farm size will lead to increase in the quantity of fertilizer purchased by about 0.1 unit of the 50 kg bag. So it's not up to 1 bag, but about 10% of that 1 bag. So nearly about 5 kgs. So now, so we see the next thing is for us, if we are interpreting, say there, this finding is in line with a priori expectation, because as the farm size as the size of the farm increases, farmer demand needs more fertilizer in order to use at the farm level. So you see that it is in line with a priori expectation. You now explain the implication. You now explain the implication of this finding, meaning that this is because if the farmer owns more large number of fertilizers are needed in order to meet the demand of the higher increasing number of the farm level. So then you now finish your analysis by saying this is in line with the findings of so. So this is one way of interpreting. In another way, some they are interpreting in a summary form, and they provide a section for discussion and implication. So they provide the general implication of all the findings. And so, but in this interpretation, you can make this one and you can summarize it in another section, only the implication. So you now write the implication of the findings and you summarize the various implications based on each of the variables. And still we should have in mind that we are only to interpret variables that are significant. So after finishing interpreting variables, coefficient of variables that are significant, we now have a last paragraph. We should say that although so and so and so variables were included in the model, but they were found to be statistically insignificant, and therefore they are irrelevant as far as explaining fertilizer demand is concerned. So this is about Euler's estimation and cost estimation test and interpretation or reporting of results. Now, the next step is hypothesis testing. Here, we want to test the hypothesis specifically. We have specific interest in answering some hypotheses we already developed in our chapter 1 as part of the objective. Maybe we write objective and we write hypothesis. So how do you test for hypothesis? So you conduct the test. It's normal t-test. You can say test, then after estimation, for example, after estimation, test, let's say income. We have specific interest in income. For example, in objective, we in chapter 1, we said that no relationship. We stated a hypothesis indicating that no relationship between income and quantity demand of the product. So now we want to test for this hypothesis. So after estimation, we are just to type tests, then we specify the variable. So you see that whether it's significant is equal to 0. This is the null hypothesis, saying that income has no impact, but we rejected it and we found that it has impact based on this probability value. So always this is t-test, and if you can see the same value as it is here, it provides the same value as it is. Probability level, you can see that it is significant at 1%. So you can test, you can also conduct ANOVA tests if you don't want the t-tests. If you don't want the t-test, so you can say ANOVA, then you write the dependent variable, which is fertilizer, like this. Fertilizer, then you write income. Sorry, I made mistake. This should be ANOVA. What happened? All right. I typed ANOVA, so you can see the results. I'm trying to make hypothesis testing using ANOVA, and we can see only income here because we are trying to test the impact of income on the fertilizer use. So fertilizer is the dependent variable in our hypothesis. So we can see the probability is saying it's not significant as far as this is concerned. So as far as this ANOVA test is concerned, the income is not significant in explaining fertilizer use. The hypothesis said that no relationship between fertilizer and income. So, as you can see, you can even use for more than two variables, for more than one variable. You can conduct the ANOVA test. For example, farm size. Farm size. So you see, there is a problem of using ANOVA command if your data contain an non-integer value. Non-integer value is a value with fraction. So you cannot do that directly unless you conduct OLS estimation. If you conduct OLS estimation, then it will give you the ANOVA table where you can be able to see the joint significance. It's the same procedure. For example, I did ANOVA for this one, I could not get. But if I do a regression, I get the value. And also you can see I get the ANOVA, the ANOVA table for this. And it is for the two variables. They are jointly significant. Based on these results, you can see the two variables are jointly significant. So it depends. If your data contain non-integer, in this case, farm size is not non-integer. Some of the observations consisted points. Some say they have 3 point something hectares. Some say they have 4 point something. So that is why you cannot directly use the ANOVA command. But if you use OLS, you have the ANOVA table for this model, OLS model. And the main target in the ANOVA is just to see the impact of the two variables together, the joint impact. So also is the same thing as explained by this table, by this F test. It is indicating the joint significance of these two variables. So otherwise, you want to use the ANOVA, so you can search for other non-integer variable, which also you already made hypothesis. For example, if I want to check, for example, laborer, income and laborer, I don't know. So you see, laborer also is an integer variable. You don't have 0 point labor, you only have 1 labor, 2 labor, 3 labor. You don't have point labor. So you can see we have done that. So you see individually, they are insignificant. Also together, this is for the together, is also insignificant jointly. So this is how you conduct ANOVA test. It's something that you use to just test the hypothesis you already developed in your study, whether there's a relationship between variables. And always you specify your hypothesis by saying, for example, income does not is not related to fertilizer demand, like this. Then you conduct the ANOVA test and you see. This is in most cases for those that are using in their research hypothesis. In most cases in economics, we usually use estimation. In many cases, especially for sectional data, we use econometric estimation. So this is about the OLS reporting, the results, interpretation, post-estimation, and ANOVA test. Now, the next in our model is a dummy variable. The next in our outline, we can see the outline, dummy dependent variables regression. In this case, we say that we want to estimate a regression model in which the variable is of two categories, in nature, or it has two categories, or is binary in nature, maybe 0 and 1, maybe yes or no. For example, in our own case, fertilizer, probably if you go to some areas, if you are talking about modern fertilizer, It's not every rural farmer that adopts fertilizer. Some of the farmers adopt modern fertilizer. Some of them, they are not capable of even adopting modern fertilizer. They are just buying the manure. They apply manure in their farming activity. So in this case, you want to estimate the determinant of fertilizer adoption. You see here, fertilizer adoption. Adoption has two categories. The variable adoption here is the dependent variable and is of two categories. Whether a farmer adopts fertilizer, modern fertilizer, or he did not adopt. Here you are not consider about the quantity purchased, just the one we did previously just now, it is quantity demand. So here is adoption. You don't care about the quantity, but rather whether he adopts or he don't adopt. So in this case, the regression model here, we say that is a dummy variable, or you can say categorical dependent variable or binary response. And in this case, you cannot use OLS, as we can remember the condition of estimation using OLS is that the dependent variable must be quantitative. So in this case, the dependent variable is categorical, it's binary, it's not quantitative. Is binary in nature, is qualitative. So you cannot use OLS to estimate it. So which model do we have? We have basically or theoretically, we have three models. We have linear probability model, we have ordered model, logic model, and we have probit model. Linear probability model, logic model, and probit model of estimation. So we are going to see this model one by one. So look at my slide. I said that meaning of binary dependent variable is how do we estimate it? So we have linear probability model. So the way you specify linear model is the way you send model. In fact, a linear probability model is a form of OLS model, but rather here the dependent variable is binary. That is why the later part of the presentation we see that this model is not in use practically. It's not in use for now practically. So you can see the dependent variable yi and the various independent. But in this case, yi is like this, not quantity, but rather is what is probability of adoption, whether it's the value is in between 0 and 1, whether it's adopted or not. So now let us, for example, estimate the linear probability model and see. Look at our data. We have fertilizer adoption, fat adoption. So this takes care of those that adopt and those that do not adopt. Those that adopt are 1, coded as 1, and those that do not adopt are coded as 0. We can even summarize to glance the information on this. You can tab. You can see minimum value is 0 and the maximum is 1. So you want to know, you can see about 27% of the farmers do not adopt modern fertilizer, and 73% of the farmers adopt modern fertilizer. So that is why in the earlier number of observations, you can see that it uses 70 something, 70 something, because for these ones, we have missing values. So now let us see to estimate our linear probability model. You type the normal OLS command regress. You now type fertilizer adoption, and then as usual you type the independent variables. For example, income, farm size, laborer, and probably years of fertilizer experience. So you can see the values here now. Looking at the results, income is no longer significant. Only laborer, number of labor used at farm is significant. So now so we can see that only this variable is significant and at 5% level. So based on this model, since it is linear model, we say 1 unit increase in 1 unit of labor in farm will lead to increase in the probability of adopting fertilizer used by 1.7%. By 1.7%, you multiply this by 100. So this is about linear probability model. However, as I said earlier, this is in theory. In practice, this is no longer being used, though it was used before. It was a popular model, but due to some practical problems, practical issues with this model is no longer in use. Actually, because of this problem, non-normality of the disturbances. The disturbance random error is non-normal. And you see that this linear probability is like OLS. You can see it is the same command. It's like OLS. Since it is like OLS, the random error need to be normal, but in this case, it's non-normal because the random error follow the Bernoulli distribution. Because at the end of the day, the random error is equals to value of dependent variable minus the actual value and the estimated value. So for this case, since the value is either 0 or 1, so that is why it follows a Bernoulli distribution. You cannot have random variables, but rather just either 0 or 1. So that is why always this random error has a non-normal distribution. Then also this error is heteroscedasticity issue, meaning that the variance of the error term in linear probability model is heteroscedastic. This is because you can see the model B plus B21, you can see the model, and this random error ultimately depends on the value of x. This one, because always after estimation, you said that you see that it is taking a particular pattern. The random error has a particular pattern to follow, because at the end of the day, the value of the dependent variable is a category. So that is why the random error is heteroscedastic in nature and never have a homoscedastic variable. One of the most big problem of this model is that non-fulfillment of this assumption. Ideally, since it is a probability, we estimated this and we interpret this as probability. Probability must lie in between 0 and 1. But if you conduct a model, if you estimate linear probability model, and you predict the y, the dependent variable, you see that in some cases, the value lies either below 0 or even above 1. If there is cases, we can try and see whether this model predicts so can we see this y hat? We can see this is above 1, while it is probability. Probability must lie below 1 and also must be above 0. And you can see above 1, this one above 1. So we can see some values. If we go through, probably we may have sometimes negative. So we can see in most cases, in some cases, they are above 1. So which makes it somehow very difficult to deal with, to represent the reality. So that is why this model actually is no longer in use, though it's one of the dummy dependent variable, but rather it's no longer in use because of this inherent issue. Number one, always the variance is heteroscedastic in nature. Number two, the random error is not normal. Number three, the probability value, possibility, it lies outside the range of probability value 0 and 1. If you predict the probability as we saw just now. So in order to get rid of this, other binary dependent models were developed. This is a logic regression model and probit regression model. So in logic regression model, the relationship between the IV and the probability is non-linear. Unlike the previous linear probability model, whereby the relationship between the independent variables and the dependent variable, that is the probability, was linear. That made it an avoidable model. So for this logic model, as we can see this expression, the relationship between the probability and the independent variables, as we can see xi, is non-linear. It's non-linear. The relationship is non-linear. However, sometimes we used to the relationship is linearized and leading to this model specification of this model. So this is how you can see after finding the log of the ratio between the probability of occurring and the probability of non-occurring, at the end of the day, you have the the relationship between the IVs and the log is linear. The log of the ratio of the probability, log of odd, this is called odd ratio. Odd ratio indicate the ratio between the probability of occurrence and the probability of non-occurrence. Probability of occurrence is the PI, non-occurrence is 1 minus PI. So the relationship between the log of this ratio has a linear relationship between has a linear relationship with the independent variables, and this is how we estimate logit model. That is why it's called logit. It means we are logging this value. We are finding the impact on this impact of this variable on the log of this variable, log of the odd. So now, how do we estimate logit model in Stata is this? And we say the condition of using logit model is when we have binary dependent variable. The dependent variable is binary in nature, is of two categories, or you call it dummy, is 0 and 1. So now already we know that the adoption of fertilizer in our data is binary in nature. So if we are in estimating model like this, we have to use logit, for example. So you type logit. Now we come to this. We check our dependent variable, which is path adoption, sorry. So we take some independent variables, maybe age, maybe income, maybe farm size, maybe labor. So in this case, we estimate. So we can see that we have our estimated logit model. And based on this result, we can see the farm size and the number of labor used are statistically significant. So you can see Stata use iteration methods, and it's present the results when it reached the minimum value of iteration, meaning that the least value of likelihood estimation, then Stata display the results. Though in the interpretation, you don't have business with this. You can even suppress this. You can even get rid of this if you want. So you can see the pseudo R square is 35, is 31. So this is trying to indicate the strength of the model is 31%. Though it's not like the R square for OLS, because in the R square for OLS is not only the strength, but it's indicating the degree of the variation explained by the independent variables for the dependent variable, meaning that the percentage of the variation in the dependent variable as explained by the independent variables. But for this one, it's just the strength. At least the model has 31% strength over 100. So we come to this. This is the estimated coefficient of the logit model. So here we say that this is significant, as said, and also this one is also significant. So if you want to interpret these results, now this is the coefficient. You follow almost nearly the same procedure as we did in the interpreting the estimated OLS model, that we have to sense in your interpretation, highlight of the variable, the level of significance, the dimension, the magnitude, conformity or otherwise with a priori expectation, the implication, and the conformity or otherwise with previous studies. But however, the language that you use to interpret this one is different from that in the OLS model. Here, for example, we see our variables that are significant is firm size. So now this coefficient, we say that okay, some is asking what is the implication of this iteration procedure? Actually, under each iteration, there is logic model. There is logic model. There is logic model. However, in theory, this logic model is one of the model that are using maximum likelihood estimation. Maximum likelihood estimation. So Stata is going to present you the logic, the result of the model that has a maximum likelihood. Or on the other way around, you said that has a minimum variance of this. If you look at this, this one is larger than this one. This one is larger than this one. This one, and this one. You can see the difference between the iteration 5 and the iteration 1 and the iteration 4 is very meager. So this is the maximum likelihood point. So that is why it is only reporting this result. But as I said, for this likelihood, there are some also results. For this also result, for this one, there are also results. But this is it, something technical actually. So it is only using the method of maximum likelihood, which is this one. This is the maximum number here, you can see. Based on this model, based on this combination of variable, so this is the maximum likelihood result that you may have. And it was indicated by Stata. So that is the implication, the iteration procedure from 0 to 5. Okay, so let's continue. So we are now trying to interpret this coefficient. So that is statistically significant. So we take the firm size, for example. We highlighted the variable. This variable is indicates the size of the farm owned by the farmer, measured in the hectares, and it was found to be statistically significant at 5% level. We can see if you multiply this by 100, you get 3.5, which is higher than 1 and lower than 5. Therefore, it is significant at 5%. So then you continue to say that this the coefficient of this variable was found to have a positive relationship with the log odd of adopting fertilizer. You can hear the language log odd is a key word here. That is why you can see the model specification here. Here we are trying to show the relationship between this one and this. Log of this. This is the odd, the probability P over 1 minus P. This is the odd ratio. So, but you have to find the log of this odd ratio. So this is what we are trying to explain now. Now here you say that there is a positive relationship between the farm size and the log odd of adopting modern fertilizer by farmer. 1 hectare increase in the farm size will lead to increase in the log odd of fertilizer adoption by 0.14 units by 0.14 units. So you then continue explaining the variable as the same we did in the OLS by saying that this is in line with a prior expectation because so this is the implication, because when there's a farm size, when the size of farms owned by a farmer enlarge, there is need for him to buy more fertilizer in order to use in the larger size of the farm. And this is in line with a previous study. You now mention a particular previous study. So this is for this farm size. For laborer also the same thing, all the same thing. The language for lodging model is that 1 unit increase in labor will lead to increase in the log out of adopting fertilizer by about 0.34 units. So this is how you interpret. Don't just say pro will increase the probability or something like that. If you do that, you are violating the theoretical model specification for lodging model. But mistakenly, if you look at different papers that are interpreting lodging model, you find out this kind of explanation. So this is not how you do. What you do is that you explain the relationship based on your measurement and log odd. If you are explaining coefficient. So now we estimate coefficient. But one thing with lodging model, you can also explain the odd ratio. You can estimate the odd ratio, not only the coefficient. For example, if I like, okay, before we estimate the odd ratio, I think we can estimate the marginal effect. So immediately after estimation, you can type MFX. So you can see the probability. This is the marginal effect. This is the marginal effect after logit. This command I use, it depends. In some Stata, you need to say MFX2. In some, just MFX, depending on the version you are using or you have. So you can see we have estimated, and this one is significant farm size and laborer. The same variables that were significant and the same are also significant in marginal effect. So this one is just probabilities. You just explain that 1% increase in farm size will lead to 0.9% increase in fertilizer purchase. You multiply this by 100. So also 1% increase in the quantity of labor on farm will lead to 2.2% increase in the quantity of fertilizer will lead to 2.2% increase in the probability of fertilizer adoption. Sorry, fertilizer adoption, not purchase. 1% increase in farm size will lead to 0.9% increase in the probability of fertilizer assumption. This one, 1% increase in the size of labor will lead to 2.2% increase in the probability of fertilizer adoption. So this is how you explain the marginal effects. Then we can also estimate odd ratio. The same model as you are estimating your lodging model, then you write comma, then you type OR, then you write enter. So this is how you get your odd ratio. You see odd ratio. Odd ratio. So there's a little difference between this and other two previous as far as the sign is concerned. Here, any value that you see is below 1, so it's negative. It's implying inverse relationship. And any value that is above 1, so it's implying a positive relationship. So if you look at our previous marginal, if you can see it has a negative sign. So the same thing as the odd ratio, we can see is below 1. So it means there is a negative or inverse relationship between age and fat adoption, though it's not significant. So now look at the p-values. We can see that the same variables, farm size and laborer, are statistically significant. So now, how do we interpret odd ratio in logic model? So here we interpret by saying one size, 1 hectare, 1 hectare of farm size, increase in farm size by 1 hectare will lead to increase in the adoption of fertilizer by about 1.16 times higher. Here we are multiplying. So this is as the same thing. So the point after is indicating the increase. That 1 increase in farm size by 1 hectare will increase the adoption of the odds of adopting fertilizer by about 1.16 times higher. You are to say this coefficient at this value times higher, the odds. For example, like this laborer, increase in 1 unit of labor will lead to increase in the adoption of fertilizer by about 1.41 unit, 1.41 times higher. Will lead to increase in the odds of adopting fertilizer by about 1.41 times higher. So this is how you interpret the odd ratio of a logic model. Assuming this is significant, the age, we can see that it is below 1, it is indicating decrease. So what we say is that 1 year increase in age will lead to the decrease in the odd of adopting fertilizer by about 0.99 times lower. So you can see this is how we interpret. So now, if we are writing our papers or we are writing for our degree oriented research, we need not only if we are estimating logic model, we need not only to present the coefficient, but rather we need to present coefficient together with either marginal effects or with odd ratio. But in most cases, since the interpretation of marginal effect is easier to do, it's better if we can present our coefficient together with marginal effect. It's easier to do because a wise man always choose something that is easier as long as you have a choice. So now, how do we report this? We are now going to do the same thing as we did in the OLS. We estimate our logic model. Remember, we have our file open. So if you are sending to the same directory, you must close this file. This you can see is previously for OLS. So before you are to send another result to this file, you have to close this. If not, it will not work. So now I close it. Already I estimated my login model. I want to send this result to what? Please, you have sent message. I cannot see. Can you send the message again? Send the question. Please send it again for me. It disappeared before I finish reading the question. Please send it again. Send the question again, please. So if you are presenting the results, or you want to send the results to Outrake 2, so you use the same. Okay. Please, if I can sense your question, you say that why is it logic model is used than probing model, and why do we you are also asking for the command for the odd ratio. So after we estimate probing model, I am going to address the issue why do we estimate logic than probe it. Please, if I cannot make the explanation, please remind me. So now So now, I want to send it to the Outrake too. So I want to call back my command. I have to indicate the directory, so I don't need to go and copy the directory again. That is why I just want to call it back. So you can see this one. And you can see I write this replace. And as I said earlier, the essence is to replace the result. If I did not write this replace, it is going to merge it with the previous OLS. So now I type this replace. So you can see that it has sent. So you can see now we are having a logit model. Logit model. So now, so I said we don't present only the coefficient as far as when we estimate a logit model. We need to either we need to merge it together with coefficient probabilities or the marginal effect or odd ratios. So now we already sent our coefficient. Now we call back our marginal effect estimation. We say MFX. So we said now instead of writing replace, we now write append. So you can see sometime I don't know whether if you can practice your own. Sometimes it repeats the same figure. So this is what we don't like. Let me try again. I estimate. I said replace. So I have only this coefficient value. So I said So let me try for the odd ratio and see whether it will not repeat the same thing as it did for marginal effects. You say outright to as you have to call back the odd ratio estimation. So here you call back our odd ratio. So now we say E form. This is if you want to export odd ratio, we need to write this E form. Otherwise, it will not export it like that. It will not. So let's check and see what will happen. So for this one, you can see it has already merged. Can we see? This is our odd ratio. So you can change the name. You can type odd ratio and so on. And so on. This is the coefficient and this is the odd ratio. So at least you can present your result like this. This column is for coefficient, is for odd ratio, and while interpreting, after interpreting the coefficient, then you summarily interpret the odd ratio. So in some cases, actually, we try to append for the probability, but you can try it and see whether it will do the same thing as it did for me. That the same figures you see, actually sometimes it does something like this. Sometimes if you restart your system, you restart your computer, you open again, it will work. It will work actually. So this is about login model. We estimate the login model coefficient. We also estimate either the probability or the odd ratio. We put it in one single table and we interpret the result. And if we cannot use this one, if it's not much, we can manually edit the table and input the figures, as you can see, for the marginal effect. If you cannot use the outright to command as it did now, I don't know, sometimes it do like that, but as I said, if you off your system, you restart your system, you use the command again, it will work. It may work probably. So now, this is about login model and interpreting login model. So now we are going for probing model. So probing model, this is also a model that has been used when you have a binary response variable. Binary dependent variable, a regression for a binary dependent variable. So just as in the case of the login model. So this is how you specify the probit model. This is the theoretical specification and this is the empirical specification. You can see fertilizer adoption and the various variables. So now we want to estimate probing model. So we write our command. You write probit So this is estimation using probing model. And you can see the coefficient. These are the coefficients. This is the probability. And you can see this is the probability of the chi-square joint significant test. And this is the pseudo R, which, as we said earlier, it indicates the strength, only the strength, not the variation, the portion of variation, but only the strength of the model. And in many cases, usually in logit and probit, you hardly have higher pseudo R square value, unlike in OLS whereby you can have higher value of adjusted R square to even 0.6, 0.7. But in this case, you only have, in many cases, relatively 0.3, 0.4, and sometimes 0.5. So we can see the log likelihood iteration. Also, the same is a method of maximum hood iteration. So you can see it presented the results at the maximum maximum likelihood. This is the maximum value compared to the rest. So this is as we said, the coefficient, and this is the probabilities. As we can see, we have three significant variables here. We have income, we have, and we have number of labor. This is significant at 10%. This one is significant at 5%. This one also significant at 5%. So now the issue is, how do we find the coefficient? So it's very difficult. Actually, it's not straightforward. Not like the previous logit and OLS. If you check different books of econometrics, it's not a direct way of interpreting the coefficient of a probing model. So this is how you can interpret. You say the coefficient give the change in disease score or probit index for a 1 unit change in the predictor. For example now, in this case, farm size. 1 hectare increase in farm size will lead to increase in the probit index by this amount, this amount, 0.089 units, meaning that farm size, 1 hectare increase in farm size will lead to increase in the probit index of adopting fertilizer by 0.089 units. So also, 1 labor increase in the farm at farm level will lead to 0.17 increase in the probit index of fertilizer adoption. You can see you are saying probit index. This is how to interpret. So also, this one you can estimate marginal effects after probits. You can see the marginal effects. This one, the same thing we explain the marginal effect from the logic model, the same thing. It's just like probability. 1% increase in farm size will lead to 1% increase. 1% increase in farm size will lead to 1.3% increase in the probability of fertilizer adoption. All things being equal, or you can say 1% increase in the amount of labor used will lead to 2.4% increase in the fertilizer adoption. So this is about logic model. So now we also need to report it. Let's try and see whether it is going to allow us to append the two tables, or it is going to repeat the figures. So I am going to close the previous one I have, because you must close before you, I don't want to save before you send another file. So I said I estimated probing model. I said this. I would like to use replace. So you can see this is the estimated probing model. So let's see whether when we append the probability it will give us. So you call back your distinct MFX. You then you now, if you want to merge it, you say append. So you can see I get the same figure, which I am not supposed to get. It is repeating the same coefficient. And this is because, as I said, for me to get the right thing now, I have to switch off my system and restart. So maybe at your own private leisure time, you can try and see what is going to happen. Then the last thing is choosing between probit logic and probit model. Which one is better? Actually, all the books, in almost all the books that talks about logic and probing model and talks about the choosing between the two model, they said it's arbitrary. There's no any criteria. It's arbitrary for a researcher either decide to use logic or probit. The only thing is that logic is more popular than the probing model because of its mathematical simplicity. It's easier to deal with logic model than the probing model. Look at the interpretation. The interpretation is in logic model is easier, it's simpler than in probing model, and also mathematical derivation, or you can say even the specification, how you specify the two models differs. So that is the reason why in most cases, logic model is more popular than the probing model because of its simplicity. Is easier to use. But in many cases, econometrics books argue that both the logic and the probing, they nearly produce the same result. I'm not saying the same 100% as in the value of the coefficient, but rather as in the number of variables that are significant, and also as in the magnitude. So they nearly give the same results, only difference is not much. So at least this is for today. I hope that I make some sense from my contribution. I'm very grateful. Thank you for listening to my presentation. Thank you. So I'm done. So I am done. Okay.
Hello, Professor. Your talk is over.
Yes, it's over. It's over, Prof.
Okay. Dear participant, if you have any question, please feel free to ask to him. I am permitted to unmute you. You can unmute yourself, or either you can raise your hand. Dear Professor, first we will deal with the questions which are in the chat box. You can see there are some questions in the chat box.
Okay. Let me check one
Yes.
by one.
And yes, one by one.
Yeah.
Are these visible to you?
Let me check. I
Yes, on
can,
the right hand
okay.
side. Yeah, on the right hand
Where?
side at the bottom, there are some
Hmm?
icons at the
Where?
bottom right hand side. Yes, please check it.
It disappeared. I can want to see. I'm checking. Okay, yes. Um, sorry, sorry. Can you see me?
Yes.
Can you see? Uh-huh. Okay. Sorry. I want to check the. So the chat is many. So I check one by one. I don't know. Some are. What happened? No sound. Good afternoon. Hi everyone. Zoom in the stars isn't enough. Zoom in the stars. It's not really enough. Zoom. Please. Hi everyone. Thank you very much. Okay, some are saying I should share the slide. I will try to do so. I will share the slide so that we get it. Prof, I will send you the slide. Okay. So please maximize. Oh, I overlooked this one. Some are saying I should maximize the slideshow, and I didn't do that. I'm sorry for that. I'm sorry for that. It was overlooked by me. Many overlooked by me. I'm sorry. Many are making complaint about the slideshare. So I can see a question that's saying, what is the implication of iteration in logic and probit? And we also already discussed about that. We highlighted that it's a method of maximum hood estimation. So it has to go through iteration processes to present the maximum hood results likelihood as explained earlier. So some is asking the difference between uh, uh, odd ratio and marginal effects. Odd ratio and marginal effect. So odd ratio, as we can see in the model specification, is just the probability, the ratio between the probability of occurrence and non-occurrence. While the marginal effect is just the probability. It's just the probability as we highlighted. The probability percentage change in the independent variable will attract a particular percentage change in the dependent variable. This is the marginal effect. The odd ratio is the ratio between the probability of occurring and non-occurring. So that is why you see if it is negative, you don't have a negative sign because it is a ratio. If it is negative, it means that the probability of occurrence is less than the probability of non-occurrence. So you see that if you divide the probability of occurrence by non-occurrence, you have the value less than 1. So that is the reason why you just multiply and say higher times higher or times lower. So maximize the starter window. So sorry for that. I didn't maximize the starter window and I didn't see the complaint until now. I'm sorry for that. I'm sorry for that actually, but not maximizing starter window. Somebody said, why the logic model is commonly used than the probit, while coefficient from these estimation techniques are almost the same. Regarding this of a logic and probit model, I think we have answered the question that is an arbitrary. It's an arbitrary. You can either use logic or probit at your own. This you don't need to conduct a specification test to choose which one is better. And in most cases, logic is commonly used because of its simplicity. Mathematically, it's simpler, and also in terms of interpretation, it's simpler. So it's also asking about why is it the coefficient from these estimation techniques are almost the same. Yes, they are almost the same. The difference is not much. If you go back to the theory, you see that there is how they presented, there's a figure, they presented the relationship whereby this one is flatter at the end, this one is steeper. So that is why the coefficient is almost the same. And actually, if you go back to Gujarat, you get more explanation on that. He made justice on this. So some is saying the command for odd ratio. If you just estimate logic model, you add comma, you write OR. So this is the command for the odd ratio. So I answered this. So Prof, I think the questions are many, and at least to the best of I answered some of the questions. So what is capital X represent on the logic model regression result? Which capital X? I don't know. I didn't see. Let me check and see if there is this capital X. So I didn't see any capital X in this one. I don't know whether you are talking about the model presentation, theoretical presentation. Here you see the X, this one. But in the result, actually, I cannot see any capital X. So if it is here, you are talking about the X here represent the variable, the independent variable. Yes. So what method of analysis will be recommended if the number of observation is less than the number of parameters? So you see, actually, as far as the cross-sectional is concerned, I don't know of the time series analysis of economics. I believe they may have a model. But for this one, I don't know any model. Somebody asks, what is the model recommended if the number of observation is less than the number of parameters? Actually, I don't know the model that takes care of that, because in most of the cases, the models available, you cannot even make this estimation. It's not possible to make this kind of estimation. Okay, Prof, thank you. I think I answer most of the questions, so I can say hello. Thank you, Prof. I don't know. Hello, Prof. Am I audible?
Yeah, you are audible, sir.
So I think. Or you want me to go to the end?
I ask,
You want me to go to the end?
I ask from the audience if they want to ask some more question.
Okay,
You
so
can
let me continue. So somebody
just
asks, what will be the solution if the
just 5 minutes
pseudo?
more. Yes,
Okay.
dear
So
participant,
somebody,
you can unmute. You have permission to unmute, or either you can raise your hand and you can ask your question from the speaker.
Hello, sir.
hello, I'm hearing you.
Okay, first of all, I would like to say thank you for your nice presentation. That was very interesting.
Thank you commenting. Thank you.
Then I have one question.
Okay.
How can we test and interpret categorical variables if the category is more than 2?
Okay. Thank you.
Okay.
So you talk about a situation whereby you have dependent variable that has more than 2 categories. So actually, because this workshop is limited to the topics of two categorical dependent variables, that is why we did not incorporate in our analysis the dependent variable that is more than 2. So in this case, you are to use other models. We have multinomial logic model, we have multinomial probing model, we have order logic model and order probing model. So depending whether the categories are in ordered ranking or not. So you use either multi or ordered. For example, if you talk about determinant of highest qualification, for example, school education qualification, you know, you attend in Nigeria, the system is primary school, junior secondary school, senior secondary school, degree, postgraduate. You see, if we make this to be categorical, we have 5 categories. So in this case, and these 5 categories are ordered. You have to finish primary before you go to junior secondary school, before you go to senior. So in this case, you are going to use either ordered logic or ordered probing model, which is not part of the discussion for this workshop. So if the categories are unordered, for example, we say determinant of clean fuel adoption. For example, we have biomass fuel, we have kerosene, we have electricity, we have gas. You see, these are 4 categories, but they are unordered. It's not they say that condition of using kerosene, you must first use biomass before you use kerosene. Condition of using electricity, you must use kerosene before you use. It's not like the primary school, secondary school we gave example before. So in this case, you use multinomial logic model or multinomial probing model. And also, thank you, your question reminded me of one thing which I did not highlight it. If
Thank you.
in our model, all our explanations, we have quantitative independent variables. We highlight independent variables that are categorical in nature. And there's a highlight between interpreting a categorical independent variable and quantitative. Maybe I can have 2 to 3 minutes to do that. I think I can do that now. I will try to estimate a model includes a variable that is categorical in nature to be one of the independent variables. So let me check this qualification, tab qualification, and see. You can see this qualification is 1, 2, 3, 4. Is categorical. So I will use it as part of independent variable so that we make the interpretation. So for example, I write this fat adoption, age, income, farm size, laborer. Let me remove this. This one. Let me remove this age. So let me use qualification. So this one, you can see the categories are 4. So in Stata, you have to set I dot. If you did not put this I dot, it will going to recognize this variable as a quantitative. What is wrong? I'm going to explain. I'm going to maybe give example on that. So you can see now the model we estimated. We can see the model we estimated. We can see qualification. How many categories now? We have 3 categories. Before, we know the variable totally has four categories, but now the result indicate 3 categories. So this is how Stata, or how you estimate model with categories. The category that is not shown, that is not appearing here, will serve as a reference category. Example now, if we say this, we are trying to explain this qualification, and we found that this category 2 is secondary school, or so if we assume it is significant, for example, for this one it's not significant, but if we assume it is significant, we now say as far as fertilizer adoption, those in secondary school, those that have secondary school certificates as their highest certificate of education, have less or a log of adopting fertilizer compared to those that did not attend school. That is the category 1 that did not appear here. We are to compare it with category 1. So we interpret this that this is negative. So this will have log of adopting fertilizer lower compared to the other category. This one is positive. This one is significant. We say that this one 3 represent those that attended degree level, school at degree level. So people that have degree as their highest level of education had higher log of adopting fertilizer by about 0.62 higher compared to those that did not attended school. That is category 1, which did not appear here. So also we did the same thing. So this is how you interpret. But let me assume that I did not write this I. I just put this qualification. Can you see that the Stata recognizes this qualification as quantitative variable, and it's wrong here? It's wrong. So in many cases, some people do not differentiate between how they use this. If you are having a categorical independent variable, and if it is more than 2 categories, you must type I dot. Otherwise, you are going to get the wrong result. But if it is 2 categories, it's okay. Even if you don't type I, either you type I or you don't type I, it will give you the same result. Because if it is 2 categories, the result is going to appear is only for 1 category. So thank you for this question.
Thank you. Thank you.
So, okay, I should continue with it's okay. So somebody asks, what will be the solution if pseudo R square is less than 50%? So you don't have to need for solution for that. If you look at Gujarati, the textbook said that it's normal to have, it's usual, it's normal to have a low value of pseudo R square. And when estimating logic model, you just present the way it is. At least if you have done the normal process to try your best, you get the less than 50%, you present it the way it is. You have nothing to do actually. Thank you.
Any more question, please? If any participant want to know. I think no more question.
Okay.
Thank you. Yeah, thank you, dear professor, for your valuable time. It's really very wonderful session. All the things which you present really wonderfully elaborated, and I hope the content which were presented in this session are really very helpful, informative, knowledgeable to all the participants who are attending this session. And along with some participants are asking about the feedback. The feedback form will be shared tomorrow. There is only one single feedback form, and that we will share tomorrow after the session. And don't worry, you will get a certificate, all the participants who are registered for this event. Now, uh, we are presenting a certificate of appreciation for this wonderful session and delivering a keynote. This certificate is proudly awarded to resource person Dr. Abubakar Hamid Danlami for imparting his valuable thoughts in 5-day international FDP on research methods in economics using Stata software. And this wonderful workshop is organized by College of Business and Economics, Mizan Tepe University, Ethiopia, in collaboration with the Department of Economics, Bahir Dar University, Ethiopia, Purnima University, India, and Mathematic Thinking Foundation, India.
Thank you. Thank you so much.
Once again, thank you, dear professor, for your valuable time and valuable thoughts which you present here. Thank you very much, and thank you all the participants who are attending this faculty development program through Cisco WebEx, and some participants are attending the session through YouTube live streaming. There are many participants who are attending there also. Tomorrow we will resume the meeting at the same time. Thank you all of you being the part of this wonderful workshop. Thank you very much.
Thank you. Thank you so much. I'm very grateful for allowing me to present. Thank you.
Thank you, Professor. Thank you.
Thank you so much. Thank you, Prof. Okay. Bye-bye. Am I free to go?
Yes, yes.
So thank you. Thank you.
Bye.
It is time to close the session.